Hello guys. Yeah, sorry I had to record this because I had to go somewhere. So welcome to session 6 of our Shor's algorithm series. So we're going to discuss in this session how to construct the quantum Fourier circuit based on the equation of the quantum Fourier transform. So we are going to start first with a 2-qubit system, and then we'll do a generalization, and after that we'll do a implement it using a 4-qubit system, which we're going to use in the next session when we discuss Shor's algorithm. So let's go to the definition. So this is the definition of a quantum Fourier transform. Let me see. Probably I'm not sharing my screen and you cannot see anything. Yeah, so I hope you're able to see that. That's the quantum Fourier transform definition. Okay, so it looks yeah, it's very compact, and but what we'll do is we'll try to take it step by step. We begin small and then we generalize. So let's begin with the first. Let's begin with 2 qubits. Okay, so if you have 2 qubits, then n is equal to 2, and we can expand this equation like this. Okay, so what you have is you have a summation. So you have 4 terms. Okay, 1, 2, 3, 4. And then what you can see also is that the y is varying from 0 to 3. Okay, that's y. While the x remains constant. And also you'll notice that the 0, the 1, the 2, and the 3, we convert them into the binary representation. So for example, 3 is 1, 1, okay, 2 is 1, 0, 1 is 0, 1, and 0 is 0, 0, okay. Now, so let me come back here. When we do this, when we do the multiplication, this is not the usual base 10 multiplication, but this one is the bitwise multiplication or the binary multiplication. So which looks like this in the next slide. Okay, so we can, if x is expressed in terms of its binary notation, and suppose that x is actually x0 x1, then x0 x1 will be expanded in this form. And we all also know that the expansion of 3 in terms of binary is we have 1 here multiplied by 2 to the 1, and another 1 here multiplied by 2 to the 0. So if you multiply this out, you will get this. Okay. So an example is if you apply the bitwise multiplication, then this one becomes like this. Okay, and this one here, if you multiply by, I mean, if you distribute the 1/2 to the to this terms here, then 2 will cancel with 4, and then the 2 and the 2 here will cancel, and then the x0 will be x0/2. And then this one here is this will actually become 1, and the reason for that is in this next slide. So the exponential of 2 pi I and x, if you write it in terms of the Euler's formula, this becomes cosine 2 pi mx plus I sine pi mx. But since the sine of a multiple of 2 pi is equal to 0, and the cosine of a multiple of 2 pi is equal to 1, then this whole expression here is just equal to 1. And by the way, the x here is always, there are only two values of x. It's either x equals 0 or x is equal to 1. Okay, it's because we are in x is a bit or a qubit. Okay, so next slide. So if we go back to the Fourier transform earlier and we expand the multiplications, okay, we will get this. Okay, so let's go back here. So if we go back to this one and apply the bitwise multiplications, okay, then you will end up with this expression. Okay, so you can see that the exponentials are already there. Okay, now we can further simplify this by combining the grouping the second term and the fourth term, so that it will look like this one here. And then if you factor out, you can actually factor out this exp x1 plus x, so you can factor this out, and then and that becomes this one here. Okay, and what you're left is that you're left with this 0 plus exponential of pi I x0. Okay, so you're left with this one here, and the first two terms, it will be like this. Okay, so it's the same, except that we just factored out the qubit, the first qubit, so which is this one here. Okay, now so you can see this becomes a common factor. The one in the under brace is a common factor, and if you factor, since it's a common factor, we can factor it out, and we are left with this expression here. So this expression is we are going to decipher that one, because that's this is an interesting expression. Okay, let me see if I'm still recording. Okay, am I still recording? Am I still recording? Let's see. Okay, so I'm still recording. Okay, now yeah, let's go to this one. So let's decipher. Okay, so the first expression, okay, this one here. Okay, let's take a look at the first expression. Okay, this one. What is this? So this one is actually nothing but a Hadamard. Okay, Hadamard gate applied to x0. Okay, so so if we have so this one is nothing but Hadamard applied to x0. Okay, so I think I will need my whiteboard in order to explain this. Okay, so let me stop sharing first. Okay, and let me show my whiteboard. Okay, so what we have is we have okay, suppose we have x0 here. Okay, so x0 can, as I mentioned earlier, x0 can either be 0 or 1. Okay, it can either be 0 or 1. So if what will be the the form of the Hadamard applied to the 0. So this one is equal to 0 plus 1, okay, over the square root of 2. And if you apply it also on 1, the qubit with value 1, it will become this one here, okay? So the only difference between them is that this one is a factor, is the sign is different, okay? So this one is if we can we can actually generalize this by saying that the Hadamard of a qubit x0 is equal to 0 plus -1 raised to the x0 and 1 here over square root of 2, okay? Because if x0 is equal to 0, this becomes 1, and you will end up with this expression. And if the value of x0 is 1, then this becomes -1, and you'll end up with this expression. Okay, so this is the form of the Hadamard. Okay, now so there is this another thing here, which in the right hand side we have 1 over the square root of 2 multiplied by 0, okay, plus the exponential of pi I, okay, x0, and then 1, okay. Now this exponential here, okay, if we go here, the exponential of pi I x0, according to the Euler's formula, this is nothing but cosine of pi x0 minus I sine of pi x0, okay? Now, as I said earlier, the value of x0 is either 0 or 1, okay? So if x0 is equal to 0, this becomes 1, okay? And this becomes 0. However, the value of x0 is equal to 1, then this becomes now cosine of pi. Cosine of pi is -1, and then sine of pi is always 0. Okay, so the value of this is -1. Okay, so when x equals 0, the value of this expression is 1. When x equals 1, the value of this expression is -1. So which means the value of exponential, which is this one, is therefore equal to 1 when x equals 0, and -1 when x is equal to -1, which is precisely this one here. Okay, so let me share my screen again. Okay, so which means that this expression is nothing but the Hadamard applied to x. Okay, now let's go to the now let's define the Pauli operator applying on 2 qubits. Okay, so suppose we have an operator V which has a subscript of ij, and then applied to a state vector which is composed of individual qubits with indexed as xn-1, xj, xi up to 0. Okay, and then the value of the result of applying the operator Vij is defined to be the vector itself multiplied by some factor. Okay, so this and so this is the definition. Okay, so we have xi xj. So this is called a controlled phase rotation operator, and then we notice that. So we know that the value of xi or xj is either 0 and 1, 0 or 1. Okay, so if either of them is 0, then the entire thing becomes 1, and this becomes the identity. Okay. However, if both of them are 1, then the this vector becomes multiplied by a phase. Okay, so we multiplied by this one here. Okay, so e to the pi I over over 2 um, absolute value of raised to the absolute value of I minus j. Okay, so let's define that kind of operator. Okay, so that's the definition. Now, so using this this definition, we can actually use that to write a this sequence of operations. Okay, so yeah, so what we're trying to do here is we are trying to derive, before we lose track. Okay, we're trying to derive this one here in terms of operators, the Hadamard operator and the Vij operator. Okay, so how does it look like? Okay, if you write this in terms of those gates, because those gates, those operators are the ones we actually know. Okay, those are the elementary operators, and what we want to do is to write the Fourier transform in terms of those elementary operators. Okay, so how does this thing look like if you write it in terms of Hadamard's and the control phase operators, which are the Vij? How does it look like? So it looks like this. Okay, so consider the following sequence of operation. Okay, so this one here, you apply it to uh, the 2-qubit system x0 x1. Okay, so one thing to notice also here, and I hope you will not be confused, is that the order of these two is very important. Okay, so what you can see here is that x0 and x1, so the order of the qubit is that the x1, the qubit with the value x1 is at the right side, and the value of the qubit with x0 is on the left side. Okay, so if you apply this, if you apply the Hadamard operator on the first qubit, okay, the 0 here corresponds to the first qubit here. Okay, this one here. Okay, so if you apply that, and then you apply this one here, the Hadamard. Okay, you apply this one. Okay, so what will happen is that you can write HO applied on x1 to be like this. Okay, so this one here, we just applied this formula. Okay, we just apply this formula. Okay, so, or I'm sorry, this formula. Okay, so exponential pi I x0. So let's go back here. So 0 plus exponential pi I x1. Okay, so x1. Okay, Now, after doing that, you can now apply apply v0 to the qubits x0 and 0. Okay, so when you do that, what happens is that um, if you apply v01 to, okay, so probably I will yeah, so probably I will stop sharing, and then let me let me explain that. Okay, so let's erase that. Okay, erase, and let's take a look. So if you have so you have 1 over square root 2 uh, 0 qubit plus exponential of pi I x1, okay, multiplied by the multiplied to qubit 1, and then suppose you apply the operator. Okay, so you have here v01 x0. Okay, so what you do is multiply this first. Okay, so multiply this, distribute. Okay, so we have v01. Let's put this outside, and then v01, and we have here x0 0 plus exponential of pi I x1, and then v01 x0 like to 1. Okay. Okay. I hope that's clear. So what happens? As we have seen earlier, if the value of one of the indices is equal to 0, then this becomes the identity. Okay, so this becomes x0 and 0. And if they are different, like for example, so here we have 0 here, and this one is x0, right? So this becomes identity. But here we have 1 and we have x0. So what happens is that, so we just bring this down, okay, x1. And what happens to this? So according to that one, this one becomes exponential of pi I x0, okay? So pi I x0, and then divided by 2, multiply, raised to the power 1 minus 0, okay? Absolute value, 1, okay? So if you bring them, if you bring it, so this one is nothing but 2 to the 1, right? So this becomes exponential. This becomes exponential of pi I. We have x1 here with x0 here over 2. Okay, so pi I x1 plus x0 over 2. Okay, and then 1. Okay, sorry, x0 1. Forgot the x0. Okay, so there must be an x0 here. Okay, there must be a 1. X0 1. Okay, and then bring down this one here, 1 over the square root of 2, and x0, 0. Okay, so that's how it looks like. Okay, let me start sharing again. Okay, let me see. Am I still recording? Yes, I'm still recording. I'm gonna share again my screen. Okay, so share screen. Okay, so that's what happens. Okay, so this is the this is what I did. Okay, in the whiteboard, and then the last operation that you want to do is apply the Hadamard to the to the uh, to the qubit at the slot 1. Okay, so if this is the qubit with index 0 and qubit index 1, so you only apply the Hadamard to the qubit indexed at 1, okay, which is x0, and the result is nothing but this one here. Okay, okay. So the result um, of applying this operator to this what you call this two qubit system is nothing but this one. Okay, so let me Control Z that so that it will be easier to see. So it's actually this one here. Okay, now what so what we'll do is we'll try to compare this one with the Fourier transform. Okay, which is in the previous page. Okay, this one here. Okay, if you compare this, okay, with this one, okay, how does it look like? So you can see that they are the same. Okay, they are the same, but this is where the important thing lies. They are the same if the order of the qubits are reversed. Okay, so we have here x0, x1, but if you go to the to this one here, the order is x1, x0. So that's very, very important to see, okay, to realize, because it's easy to make a mistake on that. Okay. Okay. So if you compare this with the application of UFT, the Fourier transform to x1, x0, they are similar except that the order of the bits are reversed. Okay. So therefore, if you measure, if you use the elementary gates, Hadamard, and the controlled phase rotation on the qubit x0, x1, and you measure it, whatever is the result, you just need to reverse the bits, okay, to get the response, to get the corresponding state that will be the result of the Fourier transform acting on x1, x0. Okay. So this is the QIS code of the visualized circuit. Okay, so let's go to the QIS. So I have here a Jupyter notebook, and then so you know and this is the result when you run this. Okay, so you create a quantum register with two qubits. Okay, so qubit 1, qubit 0, qubit 1, and then we apply Hadamard operation to the 0th qubit, okay, which is this one here, and then we apply a what you call this, the controlled phase rotation, on both 0 and 1. Okay, so this corresponds to this one here. Okay, controlled phase rotation. So this is the this is the V01, and finally this one is the H0. Okay, so applied on sorry, yeah, H0. Sorry, H1. Okay, applied on the wire number 1. Okay, so that's how it looks like. That's the this is the quantum Fourier transform circuit for a 2-qubit system. Okay, good. Now let's go now to the that's how it looks like. The generalization. Okay, so the quantum Fourier transform of an n-qubit system is generalized by its action with a computational basis. Okay, so if you have a computational basis, um, how does it look like? So so what happens is that if you this is how this is well this is the generalization of what we got here. Okay, so this is the generalization of this one is for a 2-qubit system. This one is for an n-qubit system. Now, there is an interesting notation here that I would like to point out to you. So this this notation, as you can see, this 0 dot, okay, x0, 0 dot x1, x0, 0 dot xn, dot dot dot, x2, x2, x1, x0. So that is the binary representation of a decimal. Okay, so it's called a binary decimal representation. Okay, and it's nothing but the qubits, the value of the bits on the m minus 1 position and the m minus position, and divided by 2 to the 1, 2 to the 2, 2 to the n. Okay, so this corresponds to the yeah, to this numbers here. Okay, now if you are going to apply this to a 4-qubit system, how does it look like? So if you have a 4-qubit system, it would look like this. Okay, so let's go back. So if this is the representation of a n-qubit system, where you have x0, x1, x2 up to xn, yeah, xm, and then so for a 4-qubit system, then you have x0, x1 to x3. Okay, and then what happens is that this one here, if you apply the Fourier transform, it will then give you a tensor product of a series of tensor products. Okay, so it's a tensor product, and the pattern is like this. So you begin with x0 here, and after that you have x1. It becomes x1, x0, and then it becomes x0, x1, x2, and then it becomes x3, x2, x1, x0. Okay, so that's the pattern. Okay, so that's the 4-qubit system. Okay, so I would definitely make this as an exercise, okay, for you guys. Okay. Now, so consider the following series of transformations. Okay, so this one is so what you want to do is apply the series of transformations to a a, a register containing qubits x0, x1, x2, x3. Okay, so if you do that, what will be the result? Okay, so this will actually give you this one here. Okay, so it will give you that one. Okay, and then so as you can see, if you compare this, if you compare this, if you compare this, the ordering of the bits. Okay, so here we have x3, x2, x1, x0, and so this, if you do this, you get this. If you compare that to this one, okay, what you will notice is that if this is x3, x2, x1, x0, take a look at the ordering, okay? So what you will see is that um, this one here is the reverse, okay? So we have x3, x2, x1. So x3, x2, x1, x0, and this one here is x3, x2, x1, x0. Okay, so it goes there. The ordering is reversed, and then here, so the ordering goes that way. Okay, so basically the next slide is just telling you that the result of applying the Fourier transform on this state vector is the same as applying the series of as the same as this, except that the order of the bits is reversed. Okay, so whatever, so if you apply this operation to this one, and then you measure, whatever is the result, the result, you just reverse the bits, and then what you have is already the Fourier transform of this one here. Okay, so yeah, this is the code in QIS kit. Okay, so this one is nothing but the this thing here, all this here. Okay, this is nothing but this one. Okay, so H0, V01, V02, V03, H1, V12, V13. Okay, so so this is how you transcribe it. Okay. Okay. So first you apply the Hadamard to register 0, and then you apply the controlled phase rotation for register 0 and register 1. Okay, so register 0 and register 1. Okay, okay, and then you apply the controlled phase rotation for register 0 and register 2. Okay, so register 0 and register 2. Okay, and then apply the controlled phase rotation for register 0 and register 3. Okay, so this one here, register 0 and register 3. And then you apply the Hadamard again. Okay, so here you apply Hadamard to register 1. And then you apply the controlled phase rotation for register 1 and 2. Okay, so register 1 and 2, this one here. Okay, and then register 1 and 3. Okay, so register 1, 1 and 3. Okay, and then you apply Hadamard to the to the next qubit. Okay, H2. Okay, so the next qubit is register 2. Okay, and then you apply the controlled phase rotation for qubit 2 and 3. Okay, so we have qubit 2 and 3, and finally Hadamard for the third register. Okay, and then this is what you get. Okay, a very nice drawing. Okay, so this is nothing but the quantum Fourier transform of a 4-qubit system. Okay, so that's the source code, and this one is the diagram. Okay, so now that we know how to do it, in the next session we are going to use this in order to demonstrate how RSA is able to crack the sorry, how quantum computing is able to crack the RSA for a 4-qubit system. Okay, so I think that's it, and I hope that you're able to understand my lecture, and you know, don't hesitate to message me. So I just had to go somewhere, so message me if you have any questions. Okay, thank you very much. Stop sharing and then stop recording.